Hi, everybody. So, the topic today is on RC source-free circuit. It's part of the first order circuit chapters. Okay, but I'm going to divide it out into small topics so you don't get bored, in one sessions. So RC source free. What this means is that it's a circuit that consists of resistors and capacitors. A capacitor. Okay. Before I go on, I would like to review what we did on the last topic on the capacitor. Right. Capacitor is an energy storage element. So it's very important for you to realize and always find that your capacitor, does it store any energy in it or not? To check that, right, whether your capacitor has some energy stored in it or not, you check it from the voltage across it. If there's a voltage, if you measure the voltage across the capacitor and there's some values, it means that it has some energy stored in it. Okay, so therefore you have to take that voltage into account into your circuit as you analyze it. Okay, so I will review some of the formula for capacitor first. Okay, for the voltage and current relations formula for capacitor, okay, is equal to, right, so this is the configurations. Okay, the sign conventions for it is you have a capacitor, right, with the value C, your capacitance values, the current flowing through the capacitor, there's a voltage drop across it, okay, V or VC in some of the problem. Okay, well, the formula is, right, similar to Ohm's law, right, V equal to IR, so it's related the current voltage, okay, for your resistor. So in case of capacitor, the formula is I equal to C dV dt. Okay, I equal to C dV dt. Okay, if you want to find the current across this capacitor, then you integrate it, right? So therefore, it become V equal to, right, 1 over C, integrate from certain value that you want, okay, of I, okay, plus V at T naught. So this is like your initial values, whether at T naught, okay, at the beginning, at the beginning, is there any voltage or energy stored into your capacitor or not? Okay, and of course the energy, right, depends on the voltage, so I have CV squared, energy stored in the capacitor. Okay, the capacitor, another formula that we did was, if you have a capacitor connected in series, right, then it's 1, right, 1 over C total is equal to 1 over C1 plus 1 over C2 plus, right? If you have C in parallel, if you connect capacitor in parallel, it would be C total equal to C1 plus C2 plus C3, right? Okay. So these are capacitance. Also, we have defined some rules for capacitor, right? So DC or steady state rules for capacitor is that number 1, right? Number 1. Okay. Voltage, okay, across a capacitor cannot change instantaneously. Okay, so if there's a switch, if there's a changes at T equal to 0, if, when changes at T equal to 0 in your circuit, right, that has a capacitor, VC at 0 plus, okay, is equal to VC at 0 minus. Okay, think of your phone battery, okay, your good battery in your phone, right? You fully charge, you plug into your socket. When you pull it out, your voltage in your battery still stay the same, okay, doesn't decrease right away, okay, as you pull your phone out of the socket. Okay, number two, Okay, I say it's like this, that when your capacitor is fully charged, it stays at certain values, one values. So I'll say that. So when I would say that a fully charged capacitor, okay, acts like an open circuit. Okay, so therefore, if you have a capacitor, right, and there's some V, let's say V equal to VC, and it's a constant values, okay, it's a constant value, and VC is constant value, okay, then, well, due to the formula itself, I equal to CdV dt, CdV dt, right? If your V is a constant value, then it becomes 0. So therefore, I is equal to 0 amp. So therefore, there's no current. I equal to 0. So therefore, it acts like an open circuit. So therefore, this is your V. Okay. So these are the two rules that you have to remember. So I'm going to do an example. Okay. Simple example. Just look difficult. So let's say 150 to 50 ohms plus minus 120 volt, T equal to 0, 600 ohms, 4 microfarad, 2k ohms, 100 ohms, 400 ohms, plus minus V naught. Okay. So this the problem say that, and I want to find, what do I want to find? I want to find V across capacitor, VC at 0 plus and VC at 0 minus. Okay, because the switch changes at T equal to 0 plus. Okay, so let's see. So first you look at your circuit before the switch changes at T, from minus infinities until 0 minus, right? Like if this is a timeline, right? This is a T equal to 0. From this, started from here, and it connect like this until right here, 0 minus. Okay, so let's see, I'm going to draw a picture. So it should be like this, right? 50 ohms to 50. The switch was closed, right? So plus minus 120, 600, 2k, 100, 400 ohms. Okay, well, the circuit has been like this for a long time. Currents come out, right? Go like this. Split here, charging the capacitor, V, right? VC. Okay, this one goes here, like this. Okay, well, as the time goes from negative infinity to 0, right? It's been charging, and we always assume that it's been a long time. Long enough so that your life would be easy, that okay, we can assume that it's fully charged. At T equal to 0 minus, the capacitor is fully charged. So therefore, when it's fully charged, it means that it would act like an open circuit. So we would draw this as an open circuit. It would be like this. Right? Oops, sorry. What is it? Like this. 0 minus. Okay. So therefore, if you now have to analyze this, well, VC then is nothing but, right, same as this point. So therefore, VC is a voltage drop across the 2050 ohms. Okay. Got this. Okay. Now, what is it then? Well, if you look here, okay, the voltage here across these 2 points here, right, this one and this here, is simply 120 volt. Okay, and if you write so-called, if the currents go like this, there's a plus minus like this, right? Current go like this. we can say that, well, 120 kVL in this loop, right? 120 is equal to V across 250 ohms plus VC. That means that VC is actually divided out from 120, right? The 120 volt has divided into two portions, giving itself to 250 ohms and to 1250 ohms. So you can use voltage divider, right, to find V drop across 1250 ohms. So voltage divider then would say, the formula Rx 1250, right, divided from this 120 volt and 120 volt, right, give it to all R's, which are, right, R total. So it's 250 plus 1250, and the answer is 100 ohms. So therefore, VC at 0 minus, can I write this 0, is equal to 100 ohms. What about T at 0 plus? So let's draw the circuit. It becomes like this. Right, this is open, plus minus 120. Okay, become like this. So this is VC, right? Well, but due to the rules that the voltage across the capacitor cannot change instantaneously, therefore we can write it as VC 0 plus equal to VC 0 minus equal to 100 volt. That's it. See? Okay. So that's an example. Okay. And this is also an example for you to find out what is the initial value. Oops, I said volt here. What is the initial volt, please? I wrote it wrong. Okay. What is the initial value for voltage across a capacitor? This is another way to find what is the initial values of the voltage across a capacitor. In other words, when you start solving the problem with capacitor or inductor, in this case capacitor, you have to find out if there are any energy stored in the capacitor by finding VC. Okay, that's the first thing you always do. Okay. All right, so next I would start doing RC source free. So this is a review on that. So let's do RC source free, what it is. Okay. So RC source free circuit. Okay. So I have, let's say if I have a circuit like this. Like this, okay? Okay. Okay. Switch changes at t equal to 0. All right? Okay. So, therefore, I first find the initial values. Is there any, before the switch changes to, at t equal to 0, is there any energy stored in the capacitor or not? What's VC? So at t equal to 0 minus, when I draw the picture, right, the switch still open, so we have V naught right here, R, and then C. Okay, plus minus VC, and this is C. Well, at t equal to 0 minus, we assume that the capacitor is fully charged already, so therefore the capacitor would act like an open circuit. So V naught, R, and the capacitor acts like an open circuit, VC. So you can see that in this case, VC at 0 minus, right, is equal to V naught. So there is some values, some initial values in the capacitor. Okay. So at t equal to 0, let's look at t equal to 0 plus, draw the picture, right? Well, the switch closes. Right, this. Okay, VC at 0 plus. Well, VC 0 plus is equal to VC at 0 minus, right, equal to V naught. Okay, and this is, of course, this is somehow shorted out, so we're going to forget that voltage source, and we are left with this circuit. One resistor, one capacitor, right? And no source. No source. So source free. Okay, source free circuit. So we're going to find out, I want to know, well, what happened to my VC, for this circuit, source free. I want to know, so I want to know what is V across capacitor, okay, is equal to what? As t is greater than 0. For t, for t is greater than 0. So I'm going to start now. And of course, in this chapter, you will need to have knowledge on differential equations. Hopefully this is so-called Math 3, I think. Okay, so current I, right? Assume there's a current I flowing like this, clockwise directions. I don't know yet, but I just assume that it's a clockwise directions, I. Okay, so with according to I, the voltage drop would be, well, there would be VR right here, right? V drop across R and V drop across C. Okay, so therefore, it's like a loop, right? So I'm going to write KVL for mesh I. KVL for mesh I. So it's VR plus VC equal to 0. Well, I want to get the equation to solve to be in terms of VC, V across the capacitor. So you just have to search your head. What formula do I know? What can I change? Okay, well, VC is VC. I don't want to change it anymore. Okay, what about VR? Okay, VR maybe, okay, let's start with VR. Since VR is equal to R times I, so therefore, right, R times I plus VC equal to 0, right? Okay, the current I go past R, it go past C also, the capacitor, right? And the formula relating VC and the current I is I equal to C dVC dt. So therefore, substitute I in, you get C dVC dt plus VC equal to 0. Wonderful, isn't it? VC now, everything. So therefore, I'm going to solve this. It becomes dVC dt plus 1 over RC VC equal to 0. So therefore, this is your, it's in the form of first order differential equations, with this equal to 0. I think it's called homogeneous equation, it's, I think, it's math. I forgot many of my math terms, right? So anyway, we have to solve this. And you need differential equations knowledge. Okay. Well, I'm going to use separable variable method. Okay. So dVC dt. So let's start. Equal to minus 1 over RC VC. Okay. Separable variables mean there's two variables in these equations, right? There's VC and there's a t term. So I'm going to separate them onto, in a different side of the equation, equal sign. So I want VC, right? VC equal to something. I'm going to move VC to on the left side. So therefore, and the rest, another parameter to the right side of the equal sign. So it becomes dVC, right? dVC over VC equal to minus 1 over RC dt. Right? Then, go on. What do? We want VC. Well, there's dVC, right? So I have to integrate it. So integrate both sides. So I'm going to get from 0 to t, right? Because I want the switch changes from t equal to 0 until t greater than 0. So I started from 0 to t. Well, what about VC? VC at t equal to 0 is, right, here, right? So therefore, VC at 0 is equal to V naught. So at t equal to 0, this is, right? This is a little bit bad for math. in math you should put d tau and tau equal to 0 and tau equal to t. But anyway, we are engineering, let us do it. So this is at t equal to 0, Vc is V naught, okay? And at t equal any time beyond that, it's some Vc we don't know yet. We don't know yet, right? So therefore, integrate that. Calculus, please. Calculus, integrate of dx over x equal to ln x, right? Okay, so therefore you have ln Vc, natural log, right, of V naught and some Vc of t, okay, equal to integrate of 1 over Rc, so become minus t over Rc from 0 to t, okay? So therefore, ln Vc of t minus ln V naught equal to minus t over Rc. Okay, so we want, right, ln Vc of t would be equal to minus t over Rc plus ln V naught. Okay, so therefore, to get rid of the natural log, we have to do the exponential. So therefore, at the end, your answer is Vc of t is V naught e to the minus t over Rc. So this is your answer. This is your answer, okay? So this is the answer, okay, where of course V naught is your initial values. So V naught is a voltage on a capacitor at the time the switch is changed. Move. Okay, well, the way this voltage looks like, so this is your Vc, right? So at t equal to 0, right? So e to the 0 is 1, so you have V naught. Right? And as you put in t equal to 1, t equal to 2, it would be sort of like minus exponentially going down to 0. So this is exactly, if you imagine it, your battery, right? Your battery on your phone, right? After you fully charge it, you unplug it, right? At the beginning it says 100%, right? And as it drain out, as you use it, drain out through R, okay, in this case, right? It would be that the battery use up its energy, and the voltage would drops until by the end of the day, if you didn't recharge it, it would reach 0. Okay, so this is how it looks like. Well, another important fact you have to look at is this RC right here. Okay, well, we have a definition, a name for it. Okay, so it's called a tau. Okay, so tau is called the time constant. It's a time constant. Okay, it determines, okay, time constant determines how fast the capacitor charge or discharge. In this case, it's discharging, correct? It was like at the very top, like fully charged, and then it reduces down. So this is like discharging. So sometimes we call this like discharging equations. Discharging equation, okay? So tau is a time constant. It determines the rate at which the capacitor, a capacitor, okay, charge or discharge. Okay, right? Well, for capacitor is tau equal to R times C, and the unit is second. Okay, the unit of tau is the time second. So what does 1 tau means then? 1 tau, okay, if it determines how fast things changes, right? So let's say that you are charging up to 100%. Okay, 1 tau means by a time of 1 tau, it means that 1 tau means that the charges on a capacitor change by 63%. So equivalent, like if you are fully charged at 100 volt at 1 tau it will be about 63 volt. Okay, or in terms of discharging it, okay, if you're discharging it, let's say you're discharging from 100 volt, okay, by 1 tau, this would become 37. It changes by 63%. Okay, so a small tau, you can think of that. If you have a small value of tau, it means that you have a very fast response. It decreases really fast if you're discharging it. Okay, fast response. If you have a high tau, okay, it means slow response. See, more time, it requires more time to reach steady state if you're charging it, for example, or discharging. Okay, right, so anything else? And also I want to you to see something. When we were drawing this, right, C, and we have defined this as VC, and this is VR, right, and this is IC. Okay, just the current. Doesn't have to be written as IC, just the current in the circuit. Okay, and we found out the answer VC of t to become V naught e to the minus t over RC, volt, correct? If I want to find VR, right, we started off with VR plus VC equal to 0. So therefore, VR is equal to minus VC. Correct? So therefore, my V drop across R of t is equal to minus V naught E minus t over RC. Oh, the answer turned out to be negative. So that means what? If you actually connected this, the polarity would be like this, right? Positive, negative. Okay, well, VC is positive. VC, the answer is positive, so it stays as it is. Okay, as you has assigned it before. What about current I? Current I, right? I, if you use R, I is equal to VR over R. So it's minus V naught E minus T over RC over R. M. That's the answer. Another one is another way you can calculate is I is a current. Oh, look at me. It's a capacitor. Okay, I is a current passed through a capacitor, right? So therefore the formula is I equal to C dVC by dt. Okay, so therefore it's C, right? Differentiate d dt of V naught, d parentheses V naught E minus T over RC, right? So therefore, when you differentiate that, it becomes, right, C, right? And then dip this V naught minus 1 over RC, right? E to the minus T over RC. So C cancel, right? You get minus V naught over R, E minus T over RC, M's. Oh, hopefully it's the same thing. Isn't this one? Yes. Okay. So you can see that, hey, it's a negative values also. There's a negative sign there. So it means that, what you have assigned, if you draw this, it actually goes in the opposite directions, your current. So you can imagine that, oh, what's going on here now is that your VC start with V naught, right? It has V naught in. So it becomes like a source in this circuit, and it generates, the current I come out like this, feed it through R, and then go back like this. Okay? So it's very important to sign, so be careful. All right. So let's see. Let's see an example. So find VC of t for t greater than 0 for this circuit. So VC. Okay. Okay, ready? So first, remember that you have to find out whether the capacitor has kept any energy in it or not before the switch changes. Okay, I forgot 4 ohms right here. Okay, so therefore, t equal to 0 minus, what does the circuit looks like? Okay, so draw it please. Draw it. So switch was closed, right? Capacitor. But we say that this has been for a very long time in our problems here, please. Okay, the capacitor is assumed to be fully charged, so therefore it would act like an open circuit. So this is VC at 0 minus. Okay, right? I hope that you can find VC at 0 minus for me in like 2 minutes. So you can see that VC is nothing but the voltage drop across the 6 ohms. Okay, same point here. Okay, so the circuit current flows through like this, pass through 4 ohm, go through 6 ohm. Oh, it's just one loop. So you have a mesh, right? Loop. You can use a voltage divider to find V drop across the 4 ohm and 6 ohms. So VC 0 minus equal to V drop across 6 ohms equal to 6 Rx, right? So Rx over R total times Vs. This is Vx, right? So 6 over 6 plus 4 multiplied by 20 equal to 12 volt. So VC 0 minus is equal to 12 volt. At t equal to 0 plus, what does your circuit looks like? So circuit, oops. Okay, so draw your circuit please, make it a good practice. Okay, what happened? Oh, it's open up. So 6 ohms. Oop. Hold on. 6 ohm and capacitor. VC 1 over 24 farad, 6 ohms. Okay, well, your answer, what you want is right here. This is open already, so this part of the circuit's gone. Now you have RC source free. Okay, RC source free, just like we did, things above us. Okay, in this case, of course, before we go on, we have to define that VC 0 plus then is equal to VC is 0 minus equal to 12 volt. So this is your initial values. Okay, so capacitor kept this voltage, okay, as the switch changes, right? So RC circuit, you can do the derivation just like what we did, okay, do the differential equation, integrate and blah blah blah. But if you, let's say that you did and you remember, so it's RC circuit, so therefore VC is discharging throughout 6 ohm, so it becomes V naught E minus T over RC, right? So your RC is equal to, well, there's only one resistor, which is 6 ohms, times C is 1 over 24 farad. So the answer is 1 over 4 second. So therefore, VC of t is equal to, V naught is the initial values, right? So 12 E minus T over 1 over 4. So equal to 12 E minus 4T volt. So this is the answer. Okay. So one example. Let's go for another one. Okay, another example. So find V of t for t greater than 0. Okay. Find V of t. Oh, where's my V of t? It's right here. My V of t. So it's still voltage drop across the capacitor. Just didn't write C, that's all. Okay. So same procedure. Check whether capacitor has any voltage in it or not before the switch changes. So look at t equal to 0 minus 2 ohms. switch was closed like this, and there's a 9-volt source, 4 ohms, capacitor fully charged, acts like an open circuit. So this is your circuit. So in his case, the current goes out from the source, but come to this section, junction, right? Like this, right? Supposed to go like this and like this, correct, at the junction. But in this junction, it's open right here, right? This is open, so therefore no current going through. There's no voltage drops then across it. Okay, so therefore all the currents goes in here. Okay, just for you to know, as in there's no voltage drop across the 4 ohms. So therefore the voltage drop at this point is the same as this point. The voltage at this point is the same as this point. So you measure it, V0 minus is equal to 9 volt. Okay, then at t equal to 0 plus, right, switch opens up. So 2 opens, 4 ohms, capacitor. So this 9 volt doesn't come to picture anymore because this is open, right? So now you have a capacitor, 10 microfarad, connected to the 4 ohms and the 2 ohms, 2 resistors. Okay, well, this is still V, right? V at 0 plus is equal to V at 0 minus. It's RC source free, right? 1 capacitor, but 2 resistors this time. So if you want to find tau equal to R times C. Well, which R do we take? Do we take the 4 ohms or do we take the 2 ohms? Well, of course, the answer would be we have to take both, because this is RC, so R is in the circuit, so there's 2 R's. So what did this R become? So we say that if there is more than one resistor in the RC source free, you have to calculate R equivalent. Okay, R equivalent means it's the total resistance, okay, looking from the capacitor point of view. 2 and 4 ohms, right? So looking from the capacitor point of view, okay, what are the R's that connected to that capacitor? So if you look here, right, it's equal to, it's 4 and 2 in series, so 4 plus 2 is 6 ohms. So your R equivalent is 6 ohms, so tau is 6 ohms times 10 microfarad, so equal to 60 microsecond. So therefore, at the end, your voltage in terms of V naught e to the minus t over tau would be equal to, so this answer would be, 9 e to the minus t over 60 times 10 to the minus 6, right, volt. Well, of course, you can do the reciprocal of 60 micron. Maybe you get a better, nicer values for the answer. Okay, so this is another example. So I'm going to do one last example for these sections. Okay, so the last example, V of t greater than 0. Okay, V is still easy problem, so V is still V across the capacitor. Right, so it would be nice if you actually can, sort of like, know what to do by now. Okay, what was my procedure? Okay, so the first thing is, yes, find the voltage across the capacitor before the switch changes. So draw t equal to 0 minus. So please draw it. Switch was closed, right? You can assume right now, by now, capacitor would act like an open circuit. So can you find V for me? You start. Give you like a few seconds. Right. Hopefully you can realize that the voltage drop across, you may look, oh, it's across 12, but hey, it's also across the 4 ohms because they are in parallel. So this voltage actually involve the 12 and 4 connect in parallel. So therefore, I can compress them together, and it still doesn't affect where my V is. So this is 12 parallel 4 equal to 3 ohms, right? 12 times 4 divided by 12 plus 4. Okay, so therefore, V is the voltage drop across the 3 ohms. The current come out from 24. Oh, that's it, no? We have one loop. You want to find the voltage in the circuit that's connected in series, you can use voltage divider. So therefore, V at 0 minus is equal to, V drop across the 3 ohms, so equal to 3 over 6 plus 3, right? R total times 24. So the answer is 8 volt. Next step. So write down next step, right? So picture at t equal to 0 plus, what does it look like? So therefore it would look like, actually look like this. Switch opens up, capacitor, 12 and 4 ohms, right? Plus minus V like this, 1 over 6 farad. Well, this is open, so all this doesn't come into the picture anymore. So you have RC source free again, but 2 R's. This time again 2 R's, right? So you want to find tau, so it's R equivalent times C. Okay, what's R equivalent? R equivalent, if you look from the capacitive point of view in 12 and 4, so R total is equal to 12 parallel 4. Right, so equal to 3 ohms. Oh, forgot. I should make it good practice. V at 0 plus equal to V at 0 minus equal to 8 volt. Okay, then we can find tau. Then tau is equal to 3 times 1 over 6, right, equal to 0.5 second. So with your answer, V of t, right, it's a capacitor voltage. V naught E minus t over RC. V naught is 8. E minus t over a half. So therefore, your V of t is equal to 8 e to the minus 2t volt. Finish. Okay. So that's wrap up the ideas of RC source free. Okay, RC source free. For more problems, I do it during our online, live online, okay, as exercise sessions. Okay, so that's the basic concept of RC source free. That's it. Thank you. See you later.